Hello everyone, welcome to this our Nation Science Day celebration of through X-Ray Astronomy Hands-On, very kindly brought to you by uh, two of our uh, mentors who are going to be there today, Dr. Aruberi from Indian Institute of Science Education Research, Mohali, and Dr. Chetna Jain from Hansraj College, Delhi University, both of whom have are kind of thoroughly immersed in X-ray astronomy studies, and they felt it would be good to bring it closer to young people. So that is how this, and we are joined also by two of Aru students, Vishal and Pinaki, who are going to help us through our hands-on session. So welcome all of you, Aru, Chetna, Vishal, Pinaki, and all of you participants who are going to be here. So what we are
Thank
going to
you.
do now, yeah, please, Aru, please go ahead.
No,
Uh,
I just said thank you. Thank you, Ratnashri, for nice introduction. Thank
and I am kind of a sutradhar for this. So the main work is going to be done by Aru and Chetna, and then later on by the students. I am a sutradhar, just making the wheels moving, and I'd just like to take a very little time in the beginning to walk participants through. We are here to get to know a little bit about neutron stars, and we are going to get to know about neutron stars through X-ray studies. That is the main intention of today's workshop. I'll just take a very few minutes to give a little bit of a feel to everyone about what neutron stars manifest themselves when they manifest themselves as radio pulsars. And from that, we initially got to know them. That is when the very first discovery which took place. Jocelyn Bell, who was a research student, and here is the actual her first observation of this, wherein she was looking for what are called interplanetary scintillation, just like stars. We say stars twinkle and planets don't because they're a little bit of extended bodies. They were looking for scintillation studies from quasars and extended radio galaxies and so on, and that is when something strange and which was keeping sidereal time according to the stars, which said that they are from celestial sources. And what was actually found was, this is actually it was done through chart recording, and so kind of a series of pulses about 1.3333, I mean, up to several decimal places accuracy. We got to know later on that these are those radio pulses which are coming from them. Some idea very soon emerged as to what they are, that they are kind of like dense objects, like maybe a 10-kilometer size star with the mass of the sun, and spinning around maybe an axis like this, and then a magnetic axis perhaps which is tilted from here, and for some reason through this magnetic pole, and there are plenty of reasons why it should happen, we have beams of radiation coming, and those beams of radiation, as the star rotates like a lighthouse, they come across your line of sight and give you this kind of a pulse of radiation. So that is that star merrily rotating, and it is giving out these two beams, and maybe sometimes we catch both the beams and sometimes we don't. And even the fact that we catch a beam itself, it's a low probability, right, compared to like the 360 degrees around it. We have a small beam here. So many of these neutron stars may be having these kind of structures, but we may not be seeing them as pulsars. Only when this beam crosses our line of sight, we see it as a pulsar. In addition to that, we also have, all right. I mean, a little bit more understanding of radio pulsars emerge very soon. Here we have the star, which is like the mass of the sun, but maybe in a 10-kilometer kind of radius. I'll show a very nice illustration which tells us that. And this is the spin axis, and this is the magnetic. Here it is shown as a neat magnetic field. We'll see later it gets messed up a little bit. Uh, we'll just skim through it. So here particles, very strong magnetic fields, and there is like enough this even the rotation in the magnetic field in the stars which are there. Once it condenses to so low sizes, it just increases enormously. We have huge magnetic fields, huge spins, and then charged particles are pulled out from these magnetic fields. They get pinned to these magnetic field lines. They go around it, and so they co-rotate with the star. If they co-rotate with the star, because it is so fast spin, they'll soon reach a place where it approaches the speed of light, and this is called the light cylinder. So they cannot co-rotate beyond this, and therefore there are various kinds of things which happen here, the nitty gritties of exactly why these neutron stars are shining, let's say in radio, is not known. Many theories are there, it's not finalized. But why the pulse is much simpler. Why the pulse? Because they're spinning around. Although the magnetic field may get messed up because of all these extreme conditions, they're spinning around beams of light, and we get these radio beams, and we get a lot more. Going back a little bit in time, much before this happened, when neutron itself was discovered in 1930 sometime, Bade and Zwicky immediately said, oh, perhaps end state of a star which has lost all its nuclear fuel may turn out to be a star which is just pure neutrons. And the work of Chesurun and Chandrasekhar also, it helped us enormously to understand this aspect, that when a star is actually lost all its nuclear fuel and then it is collapsing because of gravity condensing it, uh, these neutrons, now we know that when it is more than this mass, Chandrasekhar limit mass, what stops gravitation is these neutrons all, they occupy all their available quantum states, and therefore they become like hard billiard balls, and that is what happens. We understand now low mass stars may end up as a white dwarf, not very explosive death. Massive stars, explosive death as a neutron star, even more massive stars may end up as a black hole. And it is this we are interested in. And I will very quickly run through some radio observations of it. This was just an illustration to show that this object may be about not even the size of a city, right? 10 kilometers or so, an object of this kind. And this animation is from the NICER website. And the earlier animations were from astron.nl. All right. And okay, this is the interior. It's very difficult for us to know anything about the interior of this star. Though there are, theoretical speculations about this. We don't touch the interior. If you look at the radio observation, okay, a little more going back.
Sorry to interrupt, ma'am. Your slide it's not in the slideshow mode, and animations are not visible.
Oh, I see.
Yeah,
That's
yeah. Okay.
that's a little tough. All right, doesn't matter. I'll just quickly go through some of the remaining images now, and
Yes.
so
Sure.
going. I'll take just a couple of minutes more and hand over to both of you. Huh? Is that all right?
Yes. Yes. Sure. Sure.
Just 2 minutes more. So we were going back in history, right? From around 1968 when pulsars were first discovered, back in time to a theoretical understanding of them came. Go further back in time, actually go a few thousand years back, there was a star which exploded in a particular location of the sky. And it was, those days they used to be called guest stars. Those were the supernovae. And one of the supernova, this was the 1054 supernova. Much later, sometime in 18th century or so, an object of course now we are seeing this with much more detail. A fuzzy object was discovered here, which is a remnant of that supernova. And inside that remnant of the supernova, we have the compact star, which is actually giving us this radiation from the, I don't know whether this was also visible or not, but so we have all of these supernovae going about here and there. In the we see them from the we don't see them now from the galaxy, but extragalactic and so on. So do all of these supernovae have these radio pulsars or not? There are many such questions. In fact, there are many questions about radio pulsars because it's a rich field. We are not going through all of those. I'm coming back now to the very first one, which was discovered 1919 plus 16. These numbers with the neutron stars or any celestial object refer to see the first set of numbers. This is called the right ascension, and the second set of numbers is called the declination. You take the Earth's equator, throw it up into the sky. All right, and so rotation, you divide the 360-degree of rotation into 24 hours along this equator. So this 19 is out of those 24, and the 19 is the next division, hours, minutes, seconds kind of a division. So this is the right ascension. You can have another circle in the sky which is called the ecliptic, the apparent annual apparent path of the sun in the sky. This cuts this in two places, and so cuts it in the March equinox and the September equinox. So you start from the March equinox and go along the equator to get these numbers, the right ascension. And from the equator, you don't have to worry about the ecliptic, but from the equator, perpendicularly to the North Pole and to the South Pole, these angles are called the declination, which is the second number. So this was the first pulsar which was seen, and I mean by adding all the pulses according to the time period which was deduced, you get a profile maybe like this. But single pulses behave with a lot of variation, but adding up to very stable kind of profiles. And some of these pulsar sounds, if you actually they have been kind of modulated in audio. Obviously, you're not getting audio from there. This particular pulsar, the very first one, this has, I mean, modulated in some kind of sound. This was even used by for one popular music video actually. So perhaps it was for in that context that this way of sound was created for this. And pulsars have this rich structure, all kinds of profiles. Like you take that something, a camel has 5 humps, 4 humps, 3 humps. So there are many such profiles which are there for radio pulsars. And a little bit of, even though we don't fully understand what exactly is giving rise to this radiations, but we have a kind of an overall phenomenological kind of understanding that it is the magnetic field lines which are accelerating charge particles, and the curvature of these field lines is giving rise to radiation. And very beautifully this particular aspect came out through this observation. Professor Radhakrishnan and Cook, their observation that if you have a profile like this, and if you look at the polarization of the pulsar, polarization meaning that the radiation that is coming towards you is in the perpendicular direction, the electric magnetic field vectors are constrained to oscillate only, not everywhere in this field, but in some way. So if they're constrained to observe or linearly, it is linear polarization. So the angle where this is called the position angle of the linear polarization. That was seen to vary in some specific way, and this is inferred as magnetic field lines coming out like this, played out, and so you are cutting across these different angles. And this was a beautiful demonstration of this fundamental understanding of uh, radio radiation coming out. So you have profiles like this, and you have position angles like this, but individual profiles vary in this way, and there's a rich variety of phenomenon in these individual profiles. And that is like okay, this was this kind of classification Professor Joanna Rankin, where the different kinds of humps which are there for the radio pulsar profiles which we saw. And it deduced that maybe there is some kinds of rings of emission which are giving rise to, the cuts are giving rise to this. All of this is radio pulsar emission from far away. We are not reached close to this at all. So let's see how we are going to, and this is also like single pulses. This is with time, and with time, and you will see that there is rich variety of phenomenon. All of this will make us understand where radiation is coming, radio radiation perhaps. And then pulsars were also found of very small millisecond kind of periods. Now it was understood that radio pulsars, they are born maybe with high spins, but maybe who knows, maybe close to seconds or a little less, and high magnetic field, and then they slowly evolve. The magnetic field decays, period lengthens, and so on. So it was unusual to find the low magnetic field pulsar very fast spinning, which is what this was. And that brings us now to this idea that radio pulsars, here is a picture where maybe you can have the period and maybe you can have magnetic field on this axis, and you say that pulsars are born somewhere here and slowly they evolve. If the magnetic field is too low or too slow, the pulsar, they are no longer radio pulsars. However, in some cases, if these are in binary stars, they can be spun up. Mass gets transferred from the companion star to this pulsar, and as the mass get transferred, just like you can see here, water is falling on this water wheel, and slowly it makes it go faster. There. So similar to that, this pulse, this spin up happens, and therefore these stars become. These are the millisecond pulsar. Now, actually, today's workshop is going to be about those stars which are in this phase, in this mass transfer, because only then you actually see them as X-rays. X-ray emission coming from these stars, and that is where we are today. That is where our workshop is going to be. So I think this is the time for me to actually hand over to our workshop speakers, right? So I will. There were perhaps a few other aspects. Maybe, I mean, when we have some question answers, etc., I would like to go to that. Shall I hand over now to? I will hand over to the workshop speakers, and as I was saying, Aru Berry from IISER Mohali and Chetna Jain. So both of them will give you a little bit of an idea, theoretical idea about X-ray radiation that we see from from neutron stars, and then we are going to go hands-on. Aru, so shall I call you in?
Sure. Thank you, Ratnashri.
You're not going to use your video, is it? Okay, for the sake of
No, I will. I
for the sake,
can.
yeah, for the sake of bandwidth, you choose accordingly,
Uh, I
whatever you are
think I do
preferable.
have good internet speed, but if students find any lag, they can let me know or over chat or something so that I can put my video
Yeah,
off that
I
way.
actually see a few chat comments. Okay,
Actually,
slides.
there are
Oh,
no
my
chats.
slides were not changing. Oh
Yeah,
no,
so
my
thank
slides were
you.
not changing. Oh, that's sad. Really sad. All right. So maybe I will try to show them later at some stage. So you please go ahead, Aru. But I am not able to see. Chetna, are you able to see Aru's? You so probably my internet connection is not too good. Yeah,
Yes,
I
it
can
is
see.
coming. So she
Yeah,
can go
yeah.
into the slideshow mode. Yes, it
Yes,
So
is
is it
perfect.
audible
I
now?
can do it.
Yes, perfect.
Good
And
morning,
so
everyone.
from
Yeah.
for all, I just wanted to say one thing, Aru. For all our studio guests, I think if you keep your video on, I'll know that you want to come in and say something, and I will add you into it. And otherwise, I will right now leave the floor or the window to Aru. Thanks.
Okay.
Please go ahead.
Okay. Thank you. Thank you. Good morning, everyone. So, welcome to the workshop. And as the theme of the workshop is, we are going to have talk on hands-on on neutron star as observed in X-rays. So, this is a kind of a glimpse to an introduction about X-ray astronomy. My talk will be basically starting with introduction to neutron stars, and then how do we observe them in X-rays and so on. So I'll get started with my talk. So the first question is, what are the compact objects? Because as we all know that compact objects are classified or are there are different types, which are white dwarfs, neutron stars, and black holes. So in this particular workshop, we are focused on a special class of compact objects, which is neutron stars, and what exactly these compact objects are. So these are the objects which are different from a normal star, and what are those differences? In the case of normal stars, you have a nuclear fusion, which is the source of radiation pressure that balances your gravitational pull of the neutron star, and hence your star does not collapse. But then there is a life cycle for stars as well. They are also born, live, and die. So the end product of the star life cycle results into compact objects. Now, the fate of the compact object, whether it will result into white dwarf, neutron star, or a black hole, depends upon the mass of the star from which it originates. So, neutron stars, now the differences between the normal star, one of them is the nuclear fusion, which is the source of radiation, and the second difference is their compactness. And that's why they are called as compact objects. Because if you compare the mass of the compact object with a normal star, the same mass is condensed into a very small sized object. So hence they are known as compact objects. And to give you an estimate about a comparison of between the sun and different types of compact objects, in this table you observe mass, radius, mass density, and surface potential. So if you represent your solar mass as m sun, given by this symbol here, and mean density as of 1 as a reference, the surface potential or the gravitational potential of this sun is 10 raised to minus 6 times lesser compared to the strong gravitational pull of a black hole. And neutron stars, which are the theme of this workshop, lie in this range where the mass range is of the order of 1 to 3 solar mass, while the radius compared to the solar radius is of the order of 10 raised to minus 5 solar radius. And the mean density is extremely high. It's like 5 to 10 times the nuclear density. So they are extremely dense objects and they are compressed objects and hence compact objects. And the gravitational pull is also extremely high. Of course, it is lesser compared to black hole, but still huge compared to the sun or any other star, even compared to a white dwarf star. So Ratnashri gave a very nice introduction to discovery of neutron stars. So this might be a bit of repetition of the same. So neutron stars were coined first in 1933, and by these two scientists, Walter Baade and Fritz Zwicky. They proposed the existence of neutron stars to explain the origin of supernovae. So, as I've already mentioned, that the stars have a life cycle. So, supernova explosion was coined by these eminent scientists, and to explain the origin of supernova, they coined the term called neutron star, or they proposed that there exist objects like neutron stars. However, in 1967, there was a first observational evidence, which was by Jocelyn Bell and Anthony Huish, while she was working for her PhD thesis. She found the pulsations which were separated by 1.33 seconds, and she is the one who first found or discovered neutron stars in the form of radio pulsars. Now, this was an image, or a similar image was also shown by Ratnashri, and this is of a famous Crab nebula, which was produced in supernova explosion in 1054 AD. And we have a neutron star sitting at the center of this Crab nebula, which is rotating very fast with a frequency of 30 hertz. And this image is basically showing the emergence jets which are emerging from these Crab nebula, and also the plasma, the hot plasma, which is surrounding the neutron star. So we'll go into a detail of the life cycle of a star, how neutron stars are formed. So neutron stars are formed when massive stars run out of fuel and it collapses. When it collapses, the very central region of the star, this crushes every proton and electron into neutron. So basically, there is an electron capture which is going on in during this process that results into the formation of a neutron. And this is a core collapsing is between 1 to 2 solar masses. The newly created neutrons can stop the collapse. So there is the neutron degeneracy pressure which can make a balance between the gravitational pressure and the pressure, which can this degeneracy pressure will allow it to not to get collapsed further, and leaving the formation of a neutron star. So in this image, which is shown in the bottom, we have a stellar nebula. We have then formation of average star and a massive star, and then they have different phases of in their life cycle. So if you have an average star, it undergoes red giant phase, and then it results into planetary nebulae, and finally leads to a white dwarf star. And you see that mass comparison of these different compact object is there. So based on the mass of the origin, or the star from which it originates, it decides the fate of the star. So if you have a massive star, you have a red supergiant phase, and from this red supergiant phase it undergoes a supernova explosion, and then it results into neutron star or a black hole. Now if it is a very massive star, then the end product will be a massive star. But if your mass of the star, which is of the order of 1 to 2 solar masses, less about that mass, then it will result into neutron star. So we have some interesting facts about neutron stars. So what is so fascinating about neutron stars, and why do we want to study these objects? There are several interesting facts which you will be coming across during the later part of my talk. One of them is the magnetic field, and this magnetic field has a classification based on the strength, or the magnetic field. If it's of the order of 10 is by 12 to 13 Gauss, then it is very strong magnetized neutron stars, which are also known as pulsars. So we are often, in the previous talk we were talking about radio pulsars, but in the same way, we also have X-ray pulsars, and which are also classified based on their magnetic fields. So this is classification basically for X-ray pulsars, which is based on their magnetic field strength. And this is high magnetic field strength, which is of the order of 10 to the power 12 to 13 Gauss. And then we have low magnetic fields, which is of the order of 10 to the power 8 to 10 to the power 9 Gauss. Now, if you compare this magnetic field with the Earth's magnetic field, this is huge. I mean, the Earth's magnetic field is of the order of 0.25 to 0.65 Gauss, and they are extremely dense objects. So if because of their high density, even one sugar cube, which is if you place it on the neutron star, it will weighing huge. So the one sugar cube will weigh about 1 trillion kilograms when placed on neutron star, which is as huge as a mountain mass. So these dense objects are extremely important to understand, because these offer as natural laboratories to understand how these supranuclear densities exist and what are the conditions and what are the reactions which allow it to sustain and so on, which cannot be done in lab experiments like CERN or any high energy experiments which are often performed on Earth. So if you talk about the structure of the neutron star, you slice the neutron star in the form of this shape, which comes out to be a neutron star pizza shape. And you have different layers, which is something you can imagine like an onion, which has different peels. So if you peel off first layer, you have outer crust, then you have inner crust, and then you have outer core, inner core, and so on. So, and as you move towards the core, you see there is an increase in the density of the neutron star, and this is the radius of the neutron star. So it's basically cutting down the sphere into a pizza, starting from the core of the neutron star. So, do you think that when we say it's a neutron star, it is all composed of neutrons? The answer is no. We do have, solid nuclei at the outer crust. We have a mix of neutron-rich nuclei and a superfluid elements or heavy elements in the inner crust. Then we have superfluid neutrons, superfluid protons, and also we have electrons in the core, outer core. But what is there in the inner core at such huge densities is unknown. Of course, we cannot go to the neutron star and can probe into the core of the neutron star. So how we can estimate or how we can understand these densities and the core, this all signatures can come from the observations, and those observations are basically done in X-rays to understand the core of the neutron star. Of course, I'll come to that. We can understand the core from other wavelengths also, but since this is an X-ray astronomy workshop, so I'll focus on X-ray observations, how X-ray observations can reveal us the origin or composition of the core of the neutron star. And this was also mentioned by Ratnashri in her talk, that neutron star can be compressed or is of a size of a city. So we compare a neutron star to the size of a Chicago. So you see this huge density is compressed to the size of a city. So you just imagine that how dense they can be, and hence an important objects to understand the existence of such huge composition. So as I mentioned that neutron stars are classified based on their magnetic field strengths. So if they have high magnetic field strengths, then we have something called X-ray pulsars. And then you have a neutron star, we have a spin axis, you have magnetic field axis, and then you have a line of sight from which you are observing, or line of sight to the observer. So because of the misalignment between these three axes, you see the pulsations as the neutron star rotates. So these pulsations are recorded and are known as X-ray pulsations. And this is another artist impression. This is a lighthouse kind of effect from a neutron stars, which was basically for the radio pulsars, or the image which we believe for a radio pulsars. But on the right, we have the image of an X-ray pulsar, where you have a accretion. Now, if you remember or recall, Ratnashri mentioned there are different phases where there are transitions between the radio and the X-ray pulsars. So these transitions means when you have a radio pulsar active and then there is no X-ray pulsations observed, but then when there is a transition to X-ray pulsation phase, there is an accretion going on to the neutron star, and during that accretion process, you have poles of the neutron star illuminating X-rays pulsations, which we observe using X-ray instruments. The idea behind observation of X-ray pulsations and radio pulsations is the same. It's the misalignment between the axes. But here, in the case of X-ray pulsars, it is basically the mass transfer that is giving rise to the formation of X-ray pulsations. However, the origin of X-ray pulsations, radio pulsations is different compared to X-ray pulsations. Here, it's the mass transfer from the companion star, because basically in these systems, you have a neutron star which is supported, or which is in a binary system, where your companion star can be a normal type star, or it can be a B type star, or any type star which is at certain phase giving off the mass to the neutron star. And because of the magnetic field of this neutron star, it has a strong magnetic field. This magnetic field channels the mass of the neutron star onto the poles, and these poles are known as hotspots on the neutron star, which is giving you rise of X-ray pulsations. So neutron stars can be directly observed as pulsating radio sources. However, if they are gas accreting, you have periodic X-ray sources, which are X-ray pulsars. These are the few terms which I am going to show you, or repeat, basically tell you during the talk, like Eddington luminosity and so on, because during the hands-on session, you will be looking at the light curves of different sources, and a few of them will also be showing you large flares. And during those large flares, I will be telling you about Eddington luminosity. So since many of you might not be familiar with this term called what is Eddington luminosity, I thought of including it part of the talk. So what is Eddington luminosity? You have a as I already mentioned, there is a balance between a radiation pressure and a gravitational pressure that allows the electron to sustain within the sphere. So this radiation pressure, the maximum radiation pressure that can balance the gravitational pull from the mass of the star is known as Eddington luminosity. So this is the maximum luminosity. If you assume a solar mass type star, the star can have without expanding or without blowing up the electrons which is there in the atmosphere. So if you exceed this value, it's basically going to go into kind of an explosion phase, or releasing or lifting your atmosphere from the neutron star if the luminosity exceeds beyond the Eddington luminosity. So this is, in simple terms, it is the possible maximum luminosity of a star which can keep electrons from being blown out of the sphere. So if you assume a free electron which is of the mass m, and you have a star of mass m, this radiation pressure and the gravitational pressure is balancing out, and then hence your electron is within the sphere or remains in the sphere. So because of this balance, you can you have a radiation energy flux which can be written in the form of L upon 4 pi r square, where L is the energy per unit second, or it's a luminosity of the star. And if you write this equation in terms of momentum, because we have energy here, we can replace it with momentum. You finally get the momentum flux. And this momentum flux, or the mass radiation force, can then be written in terms of this expression, where sigma t is the cross section, which is Thomson cross section. and this is now expressed in terms of luminosity of the star. So the electron will remain within the sphere if the radiation pressure is less than or equal to the Eddington luminosity, and hence we get this relation. And if you assume the solar mass system, using this equation, the maximum value we obtain is of the order of 10 to the power 38 ergs per second. So this is kind of a ideal number for us to understand whether the system has undergone a Eddington or super Eddington emission accretion or not. If your X-ray luminosities are of the order of this number, then we say that it is in an Eddington phase. But if you exceed this value, let's say 10 to the power 39 ergs per second or so on, then it is basically giving you a hint that there is super Eddington accretion going on to the neutron star surface. So as I discussed earlier, that we don't have any clue about what is the composition of the core of the neutron star, and hence we rely upon X-ray observations. So how do we get that constraint on the composition of the neutron star or the so what we observe or get calculated from the observation is mass and radius estimates from X-ray observations. So these mass and radius measurements are important because they can there are several theoretical models which are proposed or based on different compositions. They can be quark matter, they can be strange matter forming the composition of the neutron star. So what exactly is the composition? Based on every model, you have different equation of state models, and different equation of state models predict different mass and radius range. And in this figure, you see the mass versus radius, and each curve is for different equation of state model proposed by different authors. So these are theoretical predictions of the neutron star composition based on the mass and radius. And you see what we want to obtain from observations is mass and radius estimates, and based then you can fit those numbers in the equation of state models and see which curves fits in well, and hence you can get the estimate about the real composition or actual composition of the neutron star. So basically your equation of state models should satisfy observations, and if they do satisfy, then you can rely upon that equation of state models. And if they are not basically coming into the or fitting into your observations, you can rule out those equation of state models. And this is how we can make a link between theory and observations to understand these supranuclear densities. So coming to X-ray astronomy and how we are using this tool or to understand the composition of the neutron star. So as you know, this is an electromagnetic band. We have spectrum all the way from radio to gamma rays. And here is the X-rays where it lies on. And as X-rays are extremely hot, the temperature range is of the order of 10 to the power 6 to 10 to the power 8 Kelvin. And as you all know that X-rays cannot reach or penetrate the Earth's atmosphere, so you have to rely upon space observations. Earlier in after the Second World War, there were observations which were, basically rocket flights and balloons were there. But now we have dedicated satellites which have instruments on board, are based upon our science goals. So the first question arises, why do we have so many satellites? The same object can be studied by one satellite also, but there are several aspects of neutron star, and not every satellite or every instrument on board satellite can satisfy all or give you answers about. So we have different science goals. Based on those science goals, we have different satellites which are launched. So we have synergies with, basically, how do we get an estimate about the neutron star or mass and radius? So if you see, this is an image of a neutron star, and this is a hotspot of kind of thing which has been formed by the mass, which is accreted onto the neutron star. And this neutron star is of a low magnetic field. So this is different from X-ray pulsars. This neutron star has a magnetic field strength of the order of 10 to the power 8 to 10 to the power 9 Gauss, and hence the X-ray, the accreted matter is not projected to the poles of the neutron star. However, it can be onto the surface of the neutron, extends to the surface of the neutron star. And as the accretion goes on, this spreading of the hotspot happens. So because of the spreading you see on the bottom panel, this is what we observe in X-rays, a profile like this during such events. You see the time scale here on the bottom axis. There's a sharp rise. So within 1 or 2 seconds, there is an increase in the count rate, and this increase can be extremely large, or abrupt increase in your count rate, and then it exponentially decays. This decay time scale can be of few tens to 100 seconds. So within this small fraction of tens or hundreds of seconds, you see a large luminosity, or they can have Eddington luminosity as well within this small brief events. And these are very important and rare transient events which are important for us to get estimates about the neutron star surface, neutron star mass and radius estimates, or the spin of the neutron star as well. So these three parameters are the three important parameters which are required to understand the composition of the neutron star. And so basically, if we try to study these thermonuclear X-ray bursts, so basically these are also known as thermonuclear X-ray bursts. Now, when we talk about X-ray, these kind of objects, these are not gravitational energy release. So when we are talking about neutron star in X-ray binaries, mostly we look at their energies in the form of gravitational energy release, which is also called as accretion energy or accretion luminosity, which is given by GMM dot by R star. But however, in contrast to those gravitational energy release, these are not gravitational energy release which happens during these events. It's a thermonuclear energy release. And if you imagine a neutron star, a nuclear reaction going on. In that nuclear reaction, the energy per nucleon which is released is of the order of 5 mega electron volt. So if that energy is compared to the gravitational energy release in the form of due to accretion is of the order of 200 mega electron volts, if it's a gravitational energy release. So 200 compared to 5 is something which will be lost in the gravitational energy release. That suggests that during these events, it is not a stable nuclear burning which happens. It's not like a simple fusion reaction which is stably burning and leading to a X-ray luminosity which is huge, but it is unstable or a runaway kind of a process which happens during these processes. So these are also known as thermonuclear runaway flashes. And if you look at these X-ray bursts in X-rays, you can study or you slice these bursts in further small segments and then fit the spectrum, which is basically your intensity versus energy information. You fit that X-ray spectrum. Ideally, they can be modeled with black body emission or black body spectra. And if you, I think the flux relation is missing, but you all know Stephen Boltzmann law. And from the Stephen Boltzmann law, there is a flux which is equated to your radius, which is on the denominator. So this is the one way. If you have a black body temperature estimates done, you can equate it with the Stephen Boltzmann law and get the radius estimate of the neutron star. So this is the important property, or this is the important types of bursts which can be studied with X-rays. And this is what I'm saying, that you can slice these thermonuclear bursts. So this is the work done by Pinaki. And this is an actual X-ray burst which has been observed with Indian X-ray astronomy, Indian multi-wavelength X-ray multi-wavelength satellite, which is known as AstroSat, which was launched in 2015. in September 2015. So it has different payloads on board Astrosat. So if you see, these are the red counters, which are known as large area X-ray proportional counters. And then you have other payloads, which is UVIT, which works in optical and UV bands. And you have SXG, soft X-ray telescope. Then you have CCTI. So these all instruments are working in different energy bandwidths, and also they do have different properties and different sensitivities. The important for us was these three red counters, which is known as LAX-BC. And these large area X-ray proportional counters are very important because for this kind of study, because they have high time resolution. And as you can see that these particular thermonuclear X-ray bursts last for only few seconds, few tenths of seconds. So which means that the counting efficiency of a detector should be extremely fast so that they can count or record large number of photons falling onto the detector. So you have a time resolution of the order of microseconds for these proportional counters, and which is excellent for this kind of study. And what we have observed is a thermonuclear X-ray burst, and then we slice this thermonuclear X-ray burst, because as you can see, the count rate is of the order of 10 raised to the power 4. So which is huge, which means even if you slice this into sub-second segment, you still have few hundreds of counts available to you to do meaningful spectroscopy or a study. So we will not go into the detail of each of the sub-segment. So basically you see there is a burst profile, which is there shown on the top panel. Then you have a temperature measurements, and these temperature measurements are done by the black body fitting. So basically your Stephen Boltzmann law is applied to the burst emission. And from that, you can estimate the radius of the neutron star. And this fourth panel is showing you the radius of the neutron star estimates. And this is the shaded region because, as I already mentioned, that we can get the spin of the neutron star measurements also by studying them in X-rays. So this was the burst oscillations or the oscillations not directly coming as you see in the pulsars, but these are the pulsations which were observed during these bursts. And these are extremely difficult to measure because of the fastness of these transient phenomena. You can see there's a fast rise, so which is like 2 seconds. Again, in that 2 seconds, to catch or to detect burst oscillations, you need excellent observatory or excellent instrument, which has a resolution of few microseconds at least, so that we can get enough counts to detect pulsations. So this is what we observed, the pulsations from the neutron star. Then we are going to talk about the strong X-ray pulsars or strong magnetized neutron stars, also known as X-ray pulsars. So as I already discussed that there is an accretion going on, and we have a hotspot which is illuminating or giving rise to X-ray pulsations. You can feel the strength of this magnetic field up to certain region around the neutron star, which is known as elfin shell or magnetospheric radius. And then you can balance out your magnetic pressure to the ram pressure, where the ram pressure is basically the accretion disk, because there's a disk which is formed around the neutron star due to accretion. And because of this balance between these two pressures, you can get the extent of the magnetospheric radius. And this magnetospheric radius, if you assume rest of the parameters to be constant, it depends upon the mass accretion rate. So this radius or the magnetospheric radius can move inwards or outwards based on depending upon your accretion rate or the mass transfer rate. And this mass transfer rate is very important, because if your accretion rate is higher, your Rm, as you can see, it is of the inverse power. It will decrease. Basically, your magnetic shell will move towards the neutron star. But if your mass accretion rate slows down, then your elfin shell will move away from the neutron star. And this is also giving an important effect on the neutron star spin, because these are accretion powered neutron stars. These are not rotation powered neutron star or internal energy powered neutron stars. So accretion is the main factor which is giving rise to X-ray pulsations or detection of X-ray pulsations. So on the bottom, we are writing an expression for the rate of change of spin frequency. As I mentioned, it's the accretion powered. So based on your mass accretion rate, your spin rate will also change. And again, if you look at this expression, if you keep rest of the parameters as a constant for a neutron star, like mass, radius, and moment of inertia, magnetic moment, and so on. So the only variable here is the accretion luminosity. And this accretion luminosity is again given by Gmm dot by R star. And m dot again is the rate of mass transfer. So this is an important factor which is deciding your rate of change of your spin frequency of the neutron star. So this is as we see the change in the intensity. So we have something called known as pulsophiles, and we'll come to the second part, which is energy dependent. So what are these pulsophiles? So as the magnetic field is channeled onto the poles of the neutron star, so we record the intensity information of this X-ray pulsations as a function of your rotational phase. So if it's a neutron star, it's rotating. If you convert your time into phase by just using that spin period information, you get the phase information. And using that phase information, you can get an information about how the intensity is varying over the rotational phase. And this graph, which is plotted against intensity versus your rotational phase, is known as pulsophiles. And as the matter is channeled onto the poles of the neutron stars with a magnetic field, you see there is this, it forms a column on the poles of the neutron, on above the neutron star. So this column is known as accretion column. And accretion column, as you see, the matter is following this column. You have different densities at different depths of this accretion column. And when at different depths, there is an interaction of your X-ray pulsations, which are coming from this hot spot, and it interacts from different depths of this accretion column, and hence it modifies the shape of the intensity profiles. And this intensity of as X-ray X-ray itself has a bandwidth which can be extending from very low to high energies, and low to high means you can have something around 0.1 keV and can go up to 100 keV or so. And based upon your energy of your X-rays, how the intensity modulates as a function of your heights of this accretion column is different. Because if it's low energy X-rays, basically there will be more interaction. It might get absorbed, it might get scattered with the matter which is inside the accretion column. And all these effects are becoming apparent in the pulsophiles which you observe in X-rays. But if they are extremely highly energetic pulsophiles, then you basically the X-rays have high penetrating effect. So they will just penetrate out from the accretion column without interaction. So they are basically simple in shape. So based upon the energy of the X-ray pulsations, X-ray pulsophiles also vary. So that's why we have high energy X-ray pulsophiles, simple in shapes, which are basically sinusoidal, a shape like sine curve. And then you can have complicated curves in lower energies. So in your hands-on sessions, you will be working with this particular source. So I just wanted to show you this particular source history. We will be giving you the X-ray data of this particular source at different phases. So one of them observation was taken in this branch, and the other was taken in this downward branch. And then there you see a kink here above around 54,000. So these times are in MJD, but if you convert this MJD into calendar date, basically around 1990, there was a spin flip taking place in this neutron star. And as if you see on the y-axis, you see there's a spin increase, frequency increase, which means it was spinning up. It was increasing its spin frequency. But then in 1990, suddenly abrupt change in the spin flip happened, and there was a decrease in the spin frequency. So we will be providing you the particular light curve, and each light curve has also different features. So that's why we selected its source for study. So you see this source during the first torque reversal. By torque reversal, I mean when the spin flip happened. And then again in 2008, there was another second torque reversal. Again, it started to increase in their spin frequency. So the spin flip happened in this particular source, and based on that, we constructed the pulse profiles. As now you know, this figure basically demonstrates the pulse profiles, which is given on y-axis the normalized intensity versus pulse phase. Now this pulse phase is basically the rotation phase, which is nothing but your time, which is converted into your rotational phase based upon the spin period, which was determined for each phase. So the important or predominant difference between these phases was, you see there are two peaks in the pulse profile or in the intensity, and these peaks were apparent in the phases which is during which the spin frequency was increasing. So this phase and this phase, the pulse profiles were resembling each other. However, in this phase, when it was going a spin flip and there was a decrease in the spin frequency, the shape of the pulse profile was different. Now, important thing is, or the important quest, apart from the composition of the neutron star or understanding the geometry of the neutron stars from the X-ray pulsars or so on, we have an important quest about studying the population of neutron stars. So, I mean, Dr. Ratnashri mentioned about radio pulsars. Then we have accretion powered pulsars, we have internal energy powered neutron stars. Then how are these different classes of neutron stars linked to each other? So we do not want to restrict to one wavelength or so on. So we want to have, joint hands to understand the population of neutron stars and how they are linked to these classes or different types of neutron stars are linked to each other. So even though we have some around 2,500 neutron stars with diverse characteristic properties, the processes responsible are different. Like you in the first talk, you heard about radio pulsars. In this, we have discussed about accretion powered. We also have internal energy powered neutron stars. By internal energy powered neutron stars, we have something known as magnetars. We have central compact objects. So basically, where the magnetic fields is giving rise to the electromagnetic radiation. So which means the origin of electromagnetic radiation is different between different classes. So our challenge is to make a unifying theme to explain this menagerie. So how these millisecond radio pulsars and at the magnetic field strengths of 10⁸ Gauss are linked to 10⁻15 Gauss magnetars or highly magnetized magnetars, and how we are going to tackle this challenge. So we have to, as I mentioned, we have to join our hands. So you might have heard about the mega projects in science. So one of them is Square Kilometer Array. So this is also an international effort with the world's largest radio telescope. As I mentioned, you need to determine the composition, to understand the composition of the neutron star, you also need to have measure of the mass. Although there are some measurements of the mass of the neutron star, but the radius of the neutron star always remain uncertain because there are several systematic uncertainties, which I did not discuss deliberately in this talk given the shortness of the time. So we need to get tackle onto the radius of the neutron star also, that how this mass is packed into small radii, and how we are be able to do that with Square Kilometer. We can measure the moment of inertia of the system or a double pulsar system with this Square Kilometer Array. And this is another way, and this can have a synergy with X-rays in the form of radius measurements, which can be done from thermonuclear X-ray bursts, which we discussed in this talk. And by doing this, we can remove several systematic uncertainties from the radius of the neutron star measurements. And hence, we can get better constraints of the composition of the neutron star. So in X-rays, we already have several X-ray satellites, which are excellent, including Indian's observatory like AstroSat. We have NICER, NewStar, observatories all working in different wavebands and also wavelengths in X-rays, and also they have different characteristics and important, and one of them is very important, which is NICER, which works in very soft X-ray energies. And I mean, we did not have such a excellent instrument in the past which works in very low energy X-rays, starting from 0.2 to 10 kV in energy regime, and with excellent time resolution, which is excellent for studying very fast X-ray pulsars, including thermonuclear X-ray bursts. So all these instruments, along with other wavelengths like SK, observatories in other wavelengths like SK, can give you a excellent estimates on the composition of the neutron star. Then we have another fourth parameter which is important for us to understand, which is X-ray polarization. Until now, we do not have any measurements about X-ray polarization. We have time information, we have energy information, we have image information, but we do lack in the polarization information about these X-rays. So we have upcoming X-ray polarization missions also, like XPOSAT and IXPE, which will be launched in near future, and then we will be able to tackle or answer several questions which are yet not answered from the understanding of the neutron stars. So with this, I will say thanks and take any questions.
Thank you, Aru. And let me just check the questions which have been coming. All of you, please feel free to ask specific to what was discussed or also overall before we have the next speaker come in. And there were some questions about what is superfluidity and about the material. Actually, maybe you, though I did answer in chat, it will be good to take this question up. Jishant was asking about the material which is falling onto the neutron star. What material is it? And he was wondering, because if it is the companion star is about to undergo a supernova, whether it is nickel kind of material, nickel iron.
So,
I said no, outside will be lighter. So maybe if you take that up.
yeah. So basically, the accreted matter which is coming onto the neutron star is hydrogen and helium gas, or it can also depend upon the composition of the companion star. If it's kind of a white dwarf star, or then you can have neon and oxygen also in the atmosphere around these stars, which can be accreted. But basically, as Ratashi already mentioned, these are light elements which are or light metals which are accreted onto the neutron star. They are not heavy elements. So basically, if you understand, if you talk about the structure of the accreted neutron star, on the top, beyond this outer crust, you have an atmosphere, which is again kind of an ocean of the hydrogen or helium like shell, which is formed above the neutron star surface.
Okay, and this was the one question was, I think, when I was talking about the beams. So that also Rahul has another question. He's saying that no, this is Ajay's question which has come. All
So
right,
I
no,
was.
Rahul's. Let me put up because that was a topic. Energy
Can.
dependence. Rahul is asking about. Can you explain more about energy dependence?
Mhm.
In which context this was, Rahul? Could you maybe specify again, or did you catch it, Aru? Which
Yeah,
context he was asking?
so I think he's talking about pulse profiles. So I'll come to that slide. One second. So I think Rahul is interested in this part where we are talking about the pulse profile dependence. As I mentioned, X-rays have different. It has a bandwidth which can extend from zero point 0.1 to 100 kV, and zero point 0.1 kV to 10 kV is known as soft X-rays. So we classify X-rays into two bands, which is soft and hard X-ray band. And when we talk about soft X-ray, so these classification is not very strict. It is basically astronomer to astronomer basis also. So zero point 0.1 to 10 kV, we call it as soft X-rays, and beyond 10 kV, we have something called as hard X-rays. And when you have soft X-rays, basically the soft X-rays, when they are coming, the radiation which is coming from this hot spot, and this there is an accretion column, as I mentioned. In the case of X-ray pulsars, your matter is coming from the accretion disk and channeled onto the poles of the neutron star. And this is the hotspot which is illuminating in X-rays. And because it is channeling onto the poles from the magnetic field strength, there is a height which is a column of certain height of few kilometers which is formed above the neutron star surface, and this column is known as accretion column. This is the column which is formed. Now when the matter of at different rates are coming onto this column, you have different speeds, and hence you have different densities across the different heights of the column, which means the matter has inhomogeneities, or there are inhomogeneities existing in this accretion column. And if you have dealing with your lower energy X-rays, which are soft X-rays, then these X-rays can interact with this material, or the material which is in the accretion column, which is basically the accreted material, which is can be of hydrogen or helium or other gases which are coming from the companion star. With this composition, it can interact, and each height will have different as it is inhomogeneous, you have different densities at different heights. And because of this interaction of your soft X-rays with this different heights, you have absorption, and light banding effects are because of the strong gravity of the neutron star. So you have different processes which modify this X-ray luminosity, X-ray flux. And because of that, you have modulation in your pulsophiles. So if you look at this pulsophile, so this pulsophile is in soft X-rays. You see there are several structures in the pulsophiles, or the pulsophile shape. You see there is a dip here, but then you have a peak here. So all these shapes are because of the modulation or the effect in this accretion column. But if you are dealing with the very highly energetic X-rays, then basically because of X-rays have a large penetrating power at higher energies, it will not interact with the absorbing material in the column. It will just escape from the accretion column without any interaction. And in that case, the shape of the pulsophiles which we often found is of the simple sine curve kind of shape. So this is the basically difference, or the energy dependence of the pulsophiles. So I hope this is clear now.
Some students are expressing they are feeling a little overwhelmed. So I have said that this could be, I mean, they could look it up again and maybe a little more preparatory material. Maybe just the context of it once more. Maybe if we just, I'll just run through. We talked about radio because my visuals were also not available. Radio pulsars, which are like, dense objects, very dense objects, and they are spinning very rapidly, and their magnetic axis may be not inclined, having an angle with respect to the spin axis. And such pulsars, they may become very slow after some time. And when such slow pulsars, you may think they won't be visible anymore. But then what happens is, if they happen to be in some kind of binary systems, mass gets transferred from the companion star onto this neutron star. And when it is falling, kind of, like, makes a disk accretion is what was being talked about. And then there may be material which is falling onto the, okay, this picture perhaps is more relevant to quasars and so on, not so much for X-ray binaries. Perhaps I did have another animation relevant to X-ray binaries, but matter is falling and getting channeled onto the magnetic poles of these stars. And as the star is rotating, you are seeing these X-ray profiles, and the data that you are going to see is kind of a time series data, right? X-ray profile data, and some of the aspects of such data, and the specific connections to the conditions onto the neutron star surface where this was falling was what was discussed about. And you could look it up again, the recorded segment of it. And when we are doing hands-on, it is this data which is there. And let me just check if there are more questions. And Gauri had this question: what is expected after some of these projects come in?
So as I mentioned, if you we are looking forward towards the future missions like exposat. Again, you see different types of pulsophiles and the shapes of pulsophiles, which are nothing but the beaming effects of the pulsophiles. So it's a beaming effect which is unknown, and you see these are electromagnetic radiation. So we have electric and magnetic fields perpendicular. So you have polarization measurements which are still lacking. You see radio polarization, which you have might have done in your hands-on session on radio pulsars also, but this information is not available to us for X-ray pulsars. So if you are able to understand this beaming effect by studying the fourth parameter, which is known as polarization, which will be able to understand the exact geometry or the beaming effect which happens during these pulsophiles. So that's why we rely upon these X-ray polarization measurements. And then coming to the other X-ray missions, like I mentioned that we need multi-wavelength or joining hands in different bands like SK, or talking about different X-ray instruments like NICER and so on. Again, the composition of the neutron star is unknown. What is there in the supranuclear densities? And these information can be obtained if you understand or study these neutron stars not in one band but in all, across all bands. And then you can get better constraints, because one band might have a certain systematic uncertainty, or by systematic uncertainty, which means like we make some assumptions when we model those observations. So, but then in different bands, you might not come across that observational uncertainty. And then if you get a similar estimates, you can get better estimates or upper limits or lower limits, or sometimes good detection of the radius of the or the mass of the neutron star or the spin of the neutron star. All these three independent measurements of three independent quantities, when measured together at different bands, can give you a better estimates about these neutron stars. And then we have several theoretical predictions like equation of state models, which is nothing but your pressure and density relationships. So how the pressure and density is related to each other based upon your mass and radius of the compact objects. So then you can model or try to see if your observations are fitting those theoretical predictions. And when you do this kind of simultaneous study, not only with observations, but joining with theoreticians, doing observations in different bands, then you get better understanding of the system. So that's why we are relying upon our future missions, and different mega science projects are there in astronomy. Okay, so there's a question from Rahul Zota saying, do we obtain the same profile for gamma rays? So no, the processes which are causing this pulse profiles in X-rays is different from gamma rays and radios. So we have different profiles in different bands. And there was a question, Ratnashri, where someone asked that he's from UG and he was not able to grasp several concepts. So I would say that there is a WhatsApp group. So we'll be able to take up his questions during that WhatsApp group through by that. And even I think during hands-on session when they will be dealing with the real data, so that time also they can come across all the questions and we can help them out. So our idea is to come outreach them, and we'll be happy to take the questions during the sessions. You're not audible. I,
Yeah, I muted myself in case of noise. Sorry about that. Yeah, we do want that all of you, I mean, maybe just listen to the this again and ask specific questions whenever you're not understanding anything. There is one question of Jishan. Maybe, Aru, if you'll take it. Meanwhile, I will put in Chetna's screen share in so that she can
sure.
get started for the next session. We're running a
Yeah.
little back in
Yeah.
time.
Yeah. How much
So,
extent in hydrogen? Okay, so you mean if I understand your question correctly, you mean how much is the extent of hydrogen helium atmosphere? So by extent, you mean the density, or I mean what is the amount of hydrogen helium? It's not very
yeah,
clear to
maybe
me.
some kind of
So
fractional amount.
yeah,
Perhaps he will
so
clarify and we'll take it up otherwise after Chetna's. Maybe he could clarify
yeah,
and we
yeah,
could
sure,
also talk to him in text chat so that
sure.
because of the
So
time
basically,
constraints.
yeah,
Yeah,
yeah. So I
please go
think
ahead.
he can take it over. So
Sorry
basically,
for
this extent depends upon the mass accretion rate. So if your mass accretion rates are higher, you can have more optical thick, or rather, I would say, if optical thick term is not clear to you, it means high density of these hydrogen helium layers on the neutron star. But if your mass accretion rate is low, because these are accretion powered systems, by accretion there's a mass transfer. So if your mass transfer is high or low, based on that your extent of hydrogen helium densities vary in these systems. So
Chetna, yeah, thanks, Aru.
I'll
Chetna, if
unmute myself now.
Yeah.
if you will go to your presentation, then I will add your screen
Yes, I'm
sharing.
going there. And due to bandwidth constraint, I am switching off the video.
Yes,
So
yes.
is my
Wait,
presentation
wait.
visible?
Yes, your presentation is visible, and so over to you.
Yeah. Thank you, Ratnashri. Thank you, Aru, for giving a very excellent theoretical background to neutron stars and X-ray emission. You've made my task very easy. And in my session, I will give you a glimpse of what is X-ray data and how we analyze such kind of a data. So the main ingredients of my talk are obviously what, why, and how. So as mentioned in the Aru's talk also, the study of astronomical objects at high frequencies, high energies of X-rays and gamma rays began around 1960s, and there is something called atmospheric windows, or simply put, the Earth's atmosphere absorbs most of the X-rays. So advances in space technology began for developing scientific payloads which can be lifted above the Earth's atmosphere, and this process started with rocket flights, then we had balloon flights, and then came the dedicated X-ray astronomy satellites like Uhuru, Exosat, RXT, Chandra, and many more. And so why are we interested in X-ray astronomy? Because data collected from these satellites, they aid our understanding of the nature of compact objects, the mechanisms by which X-rays are emitted, by the processes by which gamma rays are emitted, and these shed light on the fundamental physics of universe. So in short, this presentation or the X-ray data analysis, it will tell us about how did the universe begin, how did it evolve, what is the fate, and I will overview why are we studying all these phenomena, what is its significance. I will take you through the sources of X-ray emission and what are the mechanisms that can be studied with the observed satellite data. So there are various targets for X-ray observations. As mentioned in the previous talk also, we have X-ray pulsars, we have X-ray binaries, there are X-ray transients, and there are many more targets for X-ray emission. But for this workshop, since it's a beginner's level workshop, we'll restrict to only these three targets. So neutron stars, by now, I'm sure all of you know that neutron stars are compact objects about 10 kilometer in diameter and mass about the Chandrasekhar limit, 1.4 solar mass. And pulsars are basically rotating neutron stars. So we know that neutron stars have very intense magnetic field and particles are accelerated to tremendous amount of energies. Neutron stars may pulse when electrons are accelerated near the magnetic poles, which are not aligned with the rotation axis of the star. And as an observer, we will be able to see these pulses of radiation only when the magnetic pole is visible to us, only when the magnetic pole lies in our line of sight. By our line of sight, I imply the line of sight of the satellite, which is observing such objects. So notice one thing, remember here, that these pulses, this beam this beam of light, this is periodic. You can see from the animation, this beam of light will be towards you at a periodic rate. You remember this thing because we'll be using it in our tutorial session. The another interesting target for X-ray astronomy are X-ray binaries. Here, a companion star in the binary, this yellow big companion star, it loses material, which is intercepted by a neutron star. And this material is channeled, or it follows the strong magnetic field lines and impinges on the magnetic poles of the neutron star. The neutron star obviously will get extremely hot. The surface will get extremely hot. It so much hot that they will emit in X-rays, and we can see them as pulses due to rotation of the neutron star. So here in this animation, the material is being accreted, and then we see this violet kind of a flash, which will be observed by the observer as a pulse. Another interesting objects are the X-ray transients. Remember in the previous talk, Dr. Aru mentioned about the flashes, the nuclear burst. So these are transients which are normally not visible. They appear in the sky on and off. Whenever they are observable, they remain bright for few weeks or few days, and then they fade again. So if we are lucky enough, we can observe them, or we can point our satellites towards such sources and do some X-ray astronomy out of that. So why are we studying all this? Because answer is simple. We want to study the basic physical radiation processes that lead to generation of X-rays. And let us go, there are several processes, but we will restrict to very few basic ones so that all of you get motivated towards X-ray data analysis. So I will quickly recap the four main processes: the black body radiation, the thermal Bremsstrahlung, the synchrotron radiation, and Compton scattering. Okay, so black body radiation, all of you know that all the objects in the universe are at certain temperature and they emit electromagnetic radiation. If the temperature is sufficiently high, by sufficiently high, I imply about of the order of 10 to the power 7 Kelvin, then the radiation that is emitted, that will be predominantly in the X-ray band. The temperatures can be can lie in some other range also, but then that analysis will go in obviously some other section of the electromagnetic spectrum. We are constraining ourselves to the X-ray band. And there are several objects in our universe which have such high surface temperatures, like neutron stars, white dwarfs, the accretion disks around the compact objects in the binary system. Next comes the thermal Bremsstrahlung. So it basically implies that electron is accelerated when it passes through a charged particle. So most common situation is the emission from a hot gas as electron collides with nuclei due to random thermal motion. The thermal Bremsstrahlung produces a characteristic spectrum. Each such event produces a photon. I have specifically written this X-ray photon in some other color and bold because I want you to remember what it is for the time being. Focus on that electron is passing through the nucleus, and in the process a photon is emitted. And the energy of the photon emitted, that will directly tell us about the distribution of electrons, the energy distribution of electrons. Next comes the synchrotron radiation. Simply put, it is the electron moving in a magnetic field, moving in a strong magnetic field. So the force felt by a charged particle and a magnetic field is given by the Lorentz force, Q into V cross B. It is perpendicular to the direction of the field and to the direction of particle's velocity or the motion of the particle. So as a result, the particle moves in a circular path. And if there is an electric field also associated, obviously with in the same direction as the velocity, then we will have a spiral motion. Again, in this process, photons are emitted. I have put photon in a different font specifically. Next is simpler process, the Compton scattering. This is electron is accelerated by another photon. In this process, there is no generation of a new photon, but only scattering of photons. It can be Compton scattering or it can be an inverse Compton scattering, where photons are scattered from lower energy to higher energy or the other way around due to interaction with electrons having higher or lower energy as the case may be. So here a gamma ray photon is incident, it interacts with an electron and we have a scattered gamma ray photon and an electron. So basically this is a change in the energy of the photon. So having said this, the four basic processes, now we come to, but how will we know what is happening there? So here we have X-ray detectors, as I already mentioned, that we send our detectors on board satellites above the Earth's atmosphere, and those satellites collect data. So what is data? We do not know up till now. So this data is stored in a standard format. Like you must have heard that there is, for an image, there is a JPG format or a GIF format. So in astronomy, the data is kept in a standard format, which is called as FITS format. FITS stands for Flexible Image Transport System. This is the most commonly used format for data analysis. It is a digitally stored format in astronomy, and it stores the scientific data in multi-dimensional array and in the form of two-dimensional table. So what will you do? You will go to a certain site, the site for, as a sample, I've mentioned this site. You go there and download the data. Next step will be to reduce this data. How will you reduce this data? By using some specific software tools specific to the satellite, specific to the mission that you are using, and then you are set to go, you analyze this data. So as a sample, I'm showing you the page of this link. If you click on this site, you will end up at this page. So you go to this site, object name or coordinates, you enter the source name or the coordinates. As Ratnashree mentioned that there is certain RA and dec, right ascension and declination of the object. You can mention it here, hours, minutes, whatever is the coordinate. Enter the observation date. These for the time being, for being a beginner, you can leave the system and the search radius. Observation date. The object is there in the universe since long. The satellite has been observing it since long. You can enter here a selective range that, for example, I want to observe this particular source from 1st January 2021 to 2nd January 2021. So you will put that observation span here. There is a certain format to enter the date, year, month, and date. And you can also specify what hour and minutes and seconds of that observation span. So next is you choose the X-ray mission. There are several missions mentioned. For example, if you want to observe data collected by the Chandra satellite, you just click here, Chandra. If you want to use RXT, you click on the checkbox next to RXT. And then you download this data and reduce the data. If you had selected RXT mission, there are some softwares, some specific tools specific to this mission. You can use them and you can analyze the data. So let us come to what is data. There can be data can be in several forms. We can do timing analysis, we can do image analysis, we can do spectral analysis, and we can also do the polarization measurements. For this workshop, let us restrict to the timing analysis. So in timing analysis, data implies the number of counts. Now, what is this counts? Remember, in my previous slides, I had written X-ray photons in some other color and in a bold font. So counts means how many X-ray photons are received by the detector on board the satellite over a duration of time. Duration of time is the same one which you had entered here in the observation date. So number of photons detected by the detector over a duration of time. What will you do with this? You will create a time series. What is meant by time series? Time series means a light curve. Light curve meaning there is x-axis of it is a graph. X-axis corresponds to time, and y-axis will show you the variation of counts over that time. Obviously, this variation of counts can be random, meaning the photons are coming at their own will. It comes now, then it comes after 10 seconds, then it comes after 1 year. So 1 month, 1 day. So it can be a random process, or it can be a periodic collection of photons. I will skip the image and spectral data for this workshop. Probably we'll do it in a next series. So coming to the timing analysis, what are we trying to study? We are trying to study the variability. How are these photons being received by the detector? What is the origin of this variability? And how is the intensity changing with time? As I said, the intensity can be random. Random implies it is aperiodic. It can be highly periodic, or it can be quasi-periodic. You will know more about quasi-periodicity in the tutorial session. And how is this variation changing? That is given by the term time scale of variation. The variation can be it can be very quick variation over few milliseconds, or the variation can be of tens of years. By variation, I can mean that it is possible that for say 1 day, the number of photons received was constant within the error. And then after 1 day, the counts suddenly increased. Then the next day, the counts again settled at that constant period. So that means the time scale of variation for that particular source for that time duration will be about 1 day. So what is your goal in timing analysis? We want to identify the mechanism that is causing that kind of variability, and we want to understand what are the physical situations that are governing that kind of timing variability. Okay, so what is our starting point? Our starting point is to make a light curve. Light curve, as I said, it is for you, it is a graph between two variables. The independent variable is time. Time is plotted on the x-axis, and on the y-axis, we have the counts received. So events are placed into time bins in order to generate variation of the count rate. So what is bin size? Bin size means that while reducing the data, we can say that, okay, I want to know how much are the counts now and how much are the counts after 1 minute. So here in this example also, I've written bin size is suppose 1 minute. That is, we are collecting the number of photons after every 1 minute. 1 minute, then 2, then 3, then 4th minute. So what is the consequence of that? First is, if we are collecting information after every 1 minute, obviously we will not be able to study the variability which is less than 1 minute. We do not know what happens between 0 and 1 minute. So if there is a variability of a few seconds, we will miss that kind of a variability. And if we want to study a very long-term variability, for example, days or for weeks, then this bin size of 1 minute is redundant, meaning it will increase the file size and we will not gain on any kind of information. So the first step for you will be to generate a light curve and with an appropriate time resolution. Time resolution means with an appropriate bin size. So here are some sample light curves that you will generate in the tutorial session. These are just diagrammatic view. So random variation, x-axis is time in some unit. It can be days or it can be seconds or it can be months, depending on what kind of variability you want to study. And on the y-axis, we have counts, sometimes counts per second. It can be brightness, or you can plot it in terms of magnitude. So here in the first graph, the variation is random. We cannot see any periodicity here. There are counts this much, then it reduced, increased, reduced, increased. It is a random approach. And here delta T implies the bin size, that I am collecting the counts after every delta T time. Second graph obviously shows a periodic motion, periodic variability. The count rate was at 8, it decreased, came back to 8 again, decreased, back to 8, decreased to the same level as the previous one, and then became constant. So this shows there is some kind of periodic variation possible for this particular source. Third one, as discussed before, this shows a transient phenomena where the brightness was about 80. It suddenly increased and then there was a decay in the count rate. So we have given you different light curves where reduced light data. You have to generate such kind of light curves and experiment with different kind of bin sizes. So what is our aim? We want to look for various features in the light curve. So here the above animation is, this violet is the neutron star. This is the pulsar beam. We are looking at it face on. Whenever this beam comes towards us, there is an increase in count rate and then it becomes the nominal one. So if in your light curve, you are able to see such kind of a behavior, that means there are some periodic pulses present in this data. This data is for a pulsar. What are the other features that you can see? You can look for eclipses and transits. Now, what are eclipse and transit? Suppose we have a binary system. Binary means we have a system composed of two objects, a neutron star and a companion star. They are revolving around each other about a common center of mass. When you are able to see the two objects separately, the brightness is at maximum, this constant level. This implies that the satellite or detector is able to view the two objects separately. But once one of the components comes in front of the other or goes behind the other object, there is a decrease in brightness. Obviously, we expect a decrease in brightness. So whenever the smaller object is in front of the bigger one, the companion one, we call it as transit. And whenever it goes behind the bigger one, then that is called as eclipse. So we have given you light curves where these eclipses and transits are hidden. You have to unveil those phenomena, those features in the light curve. So for tutorial session, your first task will be to plot the light curve, plot with appropriate bin size, identify these two features, and if a burst is present, if you are looking at the light curve showing burst, you identify those features and try to determine whether there is a periodicity or not. For example, here, since this rotation is periodic, you will see this kind of a behavior in the light curve repeatedly, meaning this, then again similar after this, then similar after this. So this will tell us what is the periodicity of the system. Okay, so this was for the first task. The second step is the Fourier analysis or the power density spectrum. Now, what this basically implies is, suppose we have a light curve and we did our best, we tried several bin sizes, but still we could not find any periodicity in the light curve. Now what to do? No problem, we will generate a Fourier spectrum. So what is Fourier spectrum? We are going from the time domain to the frequency domain, and we will plot the power as a function of frequency. And you all, I'm sure you know that any signal in the time domain can be decomposed into a finite number of sinusoidal waves. So if there is any hidden periodicity in the light curve, it will appear as a strong peak in the Fourier domain. As an example, on the left hand side, I have drawn the time series, and on the right hand side is the spectrum in the frequency domain. So let us look at the first one, the top plot. Intensity versus time. Obviously, this is the light curve. Everything is juggled up. It all looks like a random variation. If there is no signal, if there is no periodicity, obviously, if you do the Fourier analysis, that is, if you plot the power as a function of frequency, you will not see any feature, any significant feature in the graph. But again, the second one, again a light curve, intensity versus time. By observation, you cannot see any periodicity in this trend, but there is something hidden. And if you go to the Fourier domain, that is, you plot the power as a function of frequency, there is a sharp peak at certain frequency. So this peak corresponds to periodicity in the signal. Then there is something called quasi-periodicity. We will come to that in the tutorial session. So again, a light curve, by looking at it, we can say, okay, there is certain, meaning this kind of a pattern is repeating, but it is not exactly a mirror image of this pattern. So it is kind of periodic, but it is not absolutely periodic. So for the time being, you can say that it is like a quasi-periodic signal. It's Fourier domain. We get a peak, but it is not as sharp as the previous one. So, but here you have to be careful that it sometimes happens that we get a peak, but it is not very significant. By significant, I imply that its power is not very large as compared to the noise level. So whenever you do a Fourier transform, always ensure that what is the significance level of this peak. And here is some real result from a source, Centaurus X3. The left panel shows the light curve meaning count per second as a function of time. Time is with respect to certain reference time, it is in seconds. So here I am showing the eclipse feature. There were certain count rates, it was varying. Then suddenly there was a drop in the count rate. So probably, and then the count rate increased. And again, I've shown only one cycle. So again, the count rates reduced. So it is kind of a periodic phenomena or the eclipse. And when I did a Fourier transform, I plotted the power as a function of frequency. There is a strong peak at a frequency of about 0.208 hertz. You invert that, invert meaning 1 upon 0.208, it will give you about 4.8 seconds. So that means the periodicity in this light curve is, in the pulsar is 4.8 second. And this second peak is the harmonic of this one. So you can see the difference between them is 0.2 hertz. So for the tutorial session, your second task will be to take the data that we have provided you, generate its power density spectrum, and determine periodicity. And I will end here. I hope you will enjoy the data analysis session and you are clear with what I have overviewed in this session. I'll be happy to take any questions.
Thank you for that very user-friendly walkthrough of what is there and what students have to do with the data to get a feel for it. So I hope I was not muted while I was saying all of this. So one question was from Rahul Zota. Can we find out whether there's any inflow of matter between the binary system from their light curve? And I was just saying that the X-rays themselves are an indication of it, and the overall periodicity from the spin. In addition to that, in X-rays you see a lot of variability over and above that, right? And that
Yes,
could
yes.
be an indication of the mass in fall.
Yes, yes.
This
We can
answer to
determine
this.
several parameters from the light curve only. Meaning for this is the beginner's one. I have kept an overview, but yes, we can determine a lot of such properties of the inflowing matter.
Okay, so there is an off-topic question about the moon, so I will answer that separately on text, given our time constraints. I'll call you in, Aru, and so we should take it. I mean, if there are further questions, we can have these discussions about that, and kind of give a final call for the moving on to the hands-on session. I need to ask both of you, should we go to one more StreamYard link for this? Are we going to kind of take a small break or continue in
We,
this? That is one
it
thing you have to do. And
is
meanwhile, any
11.
questions you have, you people can ask. Huh?
Yes, it
If
is
Pinaki and
11:15. We can take a break of 10 minutes if the participants want to, meaning they want to take a
discuss.
break, and we continue at 11:30 probably.
Yeah.
So there
And
was
we can
the
stick to this break only.
so 11:30. Then I should give the link for the next session. I will do that in the chat. Everybody, just please copy that quickly because sometimes links don't remain on YouTube. So I will do that. Aru, did you want to discuss further the question which Jishant had about the content, hydrogen, helium content, and so on? Jishant, did you clarify that anymore? Meanwhile, let me just get the link for the next session. Huh?
Yeah.
Or was there
So,
any other question any of you had? Just take a look at the chat, both of you, while I'm just trying to get the link for the next StreamYard link. Okay, I have got the link now. It was actually shared in the group as well, but I will share it here too. This is for the participants. So when we regroup, I'm putting a link out there now. When we regroup, come to this link. It's very important you copy this link, otherwise you will miss the hands-on session. And for the speakers, of course, I will give the studio link separately. I will give it to you in WhatsApp, Aru.
yeah,
Yeah.
sure. I'll forward that. And one thing, please don't hesitate if you have any questions because you all are from different backgrounds. So it will be good if you can have all queries and all doubts during the hands-on session. So it will be more interactive session. And we'll be collecting reports also at the end of the session. Basically, you can WhatsApp your PDF plots and everything through WhatsApp group. This will be good for us to know that whether you have learned or take away something at home, which is the aim of this workshop. So please try to do simultaneously. And if you're stuck somewhere, ask me, ask Chetna, or any one of the Vishal and Pinaki will also be around, so you can ask them for any help in the scripting or anything else. You have any doubts regarding science also? That is the major aspect of this workshop. So don't hesitate with any questions thinking this is not a relevant question. So all
Yes,
questions are welcome.
definitely. We encourage all of you to do the analysis along with us.
Yeah.
And it's very interesting. If you get stuck up somewhere, we'll try to, meaning, we'll help you in sharing your screen and resolve it then and there. So there is one question from Jishan
Jishan.
Salwa.
Yeah.
That eclipse is when the companion star comes in front of neutron star. Yes, Jishant, eclipse is when the companion star is in the front, and a transit is when the neutron star is in front of the companion star.
Yeah.
Yes, you were right.
Chetna, you were mentioning about the possibility of students sharing their screen. As of now, in the current condition, they will not be able to from YouTube. But when we go to the next one, we'll also share the studio link to the students. But use it very carefully because the studio can
Yes,
take only
yes.
10 people. So one by one, students can come
One
into
by
the
one.
studio,
Yes.
and then so this particular session we are Pinaki and also Vishal, if you are coming in, we will be wrapping up this part and then going to another link for the tutorial. I will send the link um, separately. All right. So, and
Yeah.
to the participants, remember, after some time, I will post the studio link in the chat. But everyone cannot rush in. You'll have to do it one by one. Okay. So, should I end this
Yeah.
broadcast here now?
Yeah.
Hmm?
Yeah.
Sure, sure.
And
Thank you.
if anyone has any concerns, so please, I hope you have all copied the YouTube link which I have mentioned. It's also there in the, and I'll immediately after this I will send you the Vishal and Pinaki. We are they are both here, so we are going to regroup very soon into the other link, and I will send that link to you. The
And we
YouTube link.
hope you all